Welcome. In today's video, we're going to look at the derivation of the moment generating function of the binomial distribution. We are then going to use this distribution to derive the first moment, the second moment, and the variance of the binomial distribution. Before we begin, let's first remind ourselves what the binomial distribution looks like. So recall, if x is distributed binomially with parameters n and p, where n is the number of trials that you are performing and p is the probability of success, then the PMF, or the probability mass function, PMF of x, is given by the following expression. Px of x is equal to n choose x, p to the power of x, 1 minus p to the power of n minus x. And recall that this expression is valid for the following sample space of x, or the following values of x. 0, 1, so on and so forth, up all the way up until n successes. So, using this expression, we can now derive the moment generating function, or the MGF. The MGF of x is given by, and let's write it down here. So our expression here is mx of t, and recall, we'll use the generic function for mx of t, or the generic expression. It is the expected value of e to the power of t multiplied by the random variable x. Now, for a discrete random variable, which the binomial distribution is, we can rewrite this as the sum across all x, or all x in the sample space, I should say, of e to the tx multiplied by the probability mass function. Then what we're going to do is we're going to substitute in our expressions. So the first element here is we're going to look at the summation, or what possible x values we can sum over. If I have a look here, we know what values we can go 0, 1, 2, all the way to the n, all the way to n. So we can rewrite this summation as x equals 0 all the way to n. We've still got our e to the tx here, and then now we're multiplying by the expression that we have above for the probability mass function, and then that's n choose x, p to the power of x, 1 minus p to the power of n minus x. And this is a fairly odd-looking expression, but we're going to do a little bit of simplification here, and hopefully we can get somewhere. It's looking a little bit scary, but I assure you we're going to get to somewhere that's quite nice. So the first thing that I notice here is I can see an e to the tx here, and I can also see a p to the x here. Now, one thing that we can rewrite this expression, in particular this e to the tx, recall from our power laws that e to the tx is the equivalent of e to the t all to the power of x. And because of this particular, when we write it in this way, we can actually combine it with the p to the x here. So what this now becomes is, in the next line, x equals 0 to n, is we still have that n choose x, but now we can combine the p and the e to the t together, and then raise all of that to the power of x. So that can become p e to the t all to the power of x, and then we still have that 1 minus p n minus x here. Now this is looking okay so far. We've sort of simplified it, but again, we're going to try and look at something. We're going to try and get this much simpler expression. This is too complicated to deal with. We can't have sigmas at the front or summation signs. So what I'm going to do, and I'm not actually going to do any manipulations, all I'm going to do is assign some parameters. And if I assign some parameters, maybe this might start looking a little bit familiar. So x equals 0, n, and on the side, the two parameters that I'm just going to assign here as an aside is I'm going to call this p e to the t. I'm going to call that just the letter a. And I'm going to call the 1 minus p, I'm going to call that b. So now, going back to my expression here, I've got n choose x. Now then that becomes a to the x. And then I've got the expression b to the n minus x. Now, this expression here hopefully actually looks a bit looks a bit familiar to you. This is actually the formula for the binomial expansion. The binomial in particular, it's the expansion of a plus b to the power of n. Now, if you're not familiar with this expansion form, I suggest that you revise this, but if you accept that this is true, or that this relationship is true, then this simply results in a plus b to the n. Now, what we can do after all that that simplification, I'm going to resubstitute in our values for b and a that we have here on the side. So this is going to become I'll put b first. Let me put b first. 1 minus p plus p e to the t to the power of n. And in fact, if you recall to the video that we had of the Bernoulli distribution, you'll notice that this expression here happens to be identical to the one of the Bernoulli distribution. Now we're just taking it to the power of n. We'll look at that in a little bit more detail when we look at sums of random variables, but this is an interesting result nonetheless. And it's a result that becomes very useful later on. I'll leave that as an aside because we're just interested in deriving now. What we're going to try and do is find the moments of the binomial distribution. We already know what those are, but we'll be interested to see if it works out using the moment generating function. So let's go on to the next page. So again, here I'm just going to rewrite our expression for the moment generating function that we derived. 1 minus p plus p e to the t, all to the power of n. So, to begin or to differ or to come up with the first and second moment, we've actually got to find the first and second derivative of this function with respect to t first. So, mx prime of t is equal to the differentiate or the derivative of our expression p e to the t, messed that one up a little bit, 1 minus p plus p e to the t all to the power of n, and I'm going to put in brackets here. So recall when we have an expression to the power of n, what we need to do is we need to bring the power down the front, then subtract 1 off the power, and then take the derivative of the inner function. So let's do that now. So we're going to bring the power down the front, that is our power of n. We're going to take 1 minus p, we're going to take our expression here, p e to the t. We've got n minus 1. And then finally, we've got to multiply by the derivative of the inner function here, which becomes 1 minus p. Again, I'm just going to write that p e to the t outside the brackets here. And then, of course, what do we have here? This 1 minus p is all a constant with respect to t, so just when differentiated with respect to t becomes 0. And when we differentiate this part here, recall the differential of e to the t, the derivative of e to the t is simply e to the t. We've got a constant out the front, you keep the constant. So bringing that all forward, that becomes n. We're going to say p e to the t at the front, just at the front here. And then we've got another expression, 1 minus p plus p e to the t n minus 1. So not a very nice derivative. It does look a little bit complicated, and the second derivative is not going to look much better, unfortunately, but let's have a crack nonetheless. We do need to, unfortunately, do it. So mx double prime of t, by definition, is the derivative of the first derivative of the moment generating function. Now, plugging in our expression here, d on dt of n p e to the t, 1 minus p plus p e to the t to the power of n minus 1. Now, notice here what we have is the product of two functions that depend on t, n p e to the t, and then this nice huge expression here. Given that we have the product, we're going to use the product rule to differentiate. So the first part is we're going to take the derivative of the first function, so npe to the t. Then we're going to just multiply that by the second expression, e to the t n minus 1. And then we're going to add the first expression, npe to the t, times the derivative of the second expression here, 1 minus p plus p e to the t, all to the power of n minus 1, and I'm just going to put it in brackets for clarity. Now, the first derivative here at the top, the derivative, that's actually quite straightforward. We can easily write that. We know that n and p are constants with respect to t, so really we're just differentiating the e to the t, and the derivative of e to the t is just e to the t by definition, so that just becomes np e to the t, and then you're left with 1 minus p plus p e to the t here, to the power of n minus 1. So that's just the first line. Second line is a little bit more complicated in the sense that we actually now still have that npe to the t out the front, but again we've got an expression for t, an expression of t inside a power. So again, we're going to use a power law, the derivative of the power, a derivative of the power to come up with our expression. So again, what we have to do is we have to take our power down the front. So then that becomes times n minus 1. That's the first part. Then we've got to take 1 off the power. So we've got our expression here again. We've got 1 minus p plus p e to the t. Now that becomes to the n minus 2. And finally, we have to take the derivative of the inner function. Now, the derivative of the inner function, I'm going to skip this step because I'm not going to express it fully. I'm just going to write down the derivative of the inner function. So if we look here in that inner function, the derivative is simply just what depends on t, just the p e to the t. The derivative of p e to the t is just times p e to the t. I thought it would be a little bit easier to handle. So, that's all good and well. Now let's see if we can come up with a common factor somewhere here. Hopefully it's possible. So the first thing I notice is these both have a common factor of np e to the t and np e to the t. Remember, there's a plus in the middle. They also have a common factor of 1 minus p plus p e to the t n minus 2. Here implicitly it's also here because you could rewrite this as minus 2 plus 1. And then this plus 1 would come outside the brackets, or you could expand that a little bit. So let's try and take this out as a common factor. In fact, let me do one more line of working to show you how it is a common factor, just so it's a bit more clear. So you have the np e to the t, this is from the top. Then you can rewrite this 1 minus p plus p e to the t n minus 1. That can actually be rewritten as 1 minus p plus p e to the t to the power of n minus 2, and then multiplied by 1 minus p plus p e to the t. Again, because this is theoretically to the power of 1, and then using our power laws, we've got the 1 plus the n minus 2 gets you back to n minus 1, hence why we can write it in that expression. For now, I'm just going to remove that power, so it's a bit more cleaner. Then we've also got the np e to the t. We've got that expression for 1 minus p plus p e to the t n minus 2. And finally, we have this expression for n minus 1, and we have this expression for p e to the t. So what I'm going to do there is I'm just going to multiply by n minus 1 p e to the t. After all of this, what I'm going to do is I'm going to combine these two expressions, taking a common factor out now of this expression here that I have. So that simply becomes np e to the t. You've got the 1 minus p plus p e to the t to the n minus 2. Whew, it's a bit of a doozy. And then we've got to multiply. Now again, we're factoring this out, so we're just going to add these two last terms together. So that becomes 1 minus p plus p e to the t plus n minus 1 p e to the t. Oh, bit of a lengthy problem here, but it's good practice of our derivatives. So again, we're just going to simplify that last component here because I think we can do a little bit of simplification. So np e to the t at the front, we've still got the 1 minus p plus p e to the t n minus 2. And then finally at the back, we've got multiplied by. Now, here in our expression, our 1 minus p, that's not going to change, so we're going to have a 1 minus p here. What you do notice here is there's a positive p e to the t here. But then, if we expand the brackets here, on this side, we've got a negative p e to the t when we expand those brackets. So effectively, this PET, positive PET, will cancel out with the negative PET at the back. So therefore, we're just left with n times p e to the t. And so that's what I'm going to write, n p e to the t. And we've come up with our first and second derivative. Now it's time to calculate the first and second moments. So let's see if we can do that. Now going back here, the first moment of x, if you recall, the expected value of x, is the first derivative of the moment generating function evaluated at 0. Now I'm just going to put in our expression that we derived before, so that became np p e to the t. Then we've got 1 minus p plus p e to the t to the power of n minus 1. Sorry, got that. And then that is evaluated at t is equal to 0. So let's plug all of this in. This becomes n p e to the 0 minus 1 minus p plus p e to the 0 to the power of n minus 1. Now, e to the power of 0, there's 2e to the power of 0s. They simply just become 1, because anything to the power of 0 is 1. So you've got np, 1 minus p, and then here you've got p times 1, so it just becomes plus p to the power of n minus 1. After a bit of simplification, this just becomes np1 to the n minus 1. And we know that 1 to the power of anything is simply equal to 1, so we're left with np. And although that was a complicated expression, we have arrived at what we do know to be the first moment of the expected value of the binomial distribution, simply equal to the number of trials times the probability of p success, or the probability of success. So now let's have a look at the second moment of the binomial distribution. We can calculate that again as the second derivative evaluated at 0. So let's do that now. Firstly, let me substitute in my expression. So I derived this expression before, npe to the t, 1 minus p plus pe to the t to the n minus 2. And then finally I had at the back 1 minus p plus npe to the t. So and don't forget, this is evaluated at t equals 0. So let's substitute that in now. npe to the 0, 1 minus p plus pe to the 0 to the power of n minus 2. Then we've got 1 minus p plus np e to the 0. Doing a little bit of cleaning up again. E to the 0 is just 1, so that becomes np. Here, again, very similar occurrence occurring. You've got p e to the 0. The e to the 0 is 1. That just becomes p, that whole expression. You got minus p plus p. You're just left with 1. So in fact, what I'm going to write that is dot 1 to the power of n minus 2, quite simply. And then on this side of the equation, what we've got is times 1 minus p plus np. Pretty straightforward expression. And finally, this can simplify down to, again, 1 to the power of anything is 1. I'm just going to leave that expression as is. And so this our expression now becomes np multiplied by 1 minus p plus np. Quite straightforward, not straightforward, but we've got somewhere. We've evaluated the second moment, so let's just finally do the final moment, or the variance, I should say, not the final moment, but the variance. Recall that the variance of x is equal to the expected value of x squared minus the expected value of x squared. Putting our expressions in, we have we had np 1 minus p plus np for the expression that we had before, and then we have np all squared. And if you have a look here, these actually have a common factor of NP. Sorry, and we substituted the expected value of x, which is NP. Now these have a common factor of NP, as you can see here. So we're going to take that out as the common factor. So that becomes NP 1 minus P plus NP. And then we've got to subtract NP out as that factor. These two cancel out, the plus NP and the negative NP, or the minus NP, and that gives you NP 1 minus P, which we do know to be the variance of the binomial distribution. Very, very complicated derivatives, very complicated substitutions, but we have arrived at the results that we expected. Thank you for watching, and hope to see you in the next video.